Okay, so this week we have 5 problems again, and let's get to it. Okay, I'm assuming that you read the problems. The first problem, it's fairly straightforward, I think. Um, you're given two numbers up to 10 digits, non-negative integers, and you're trying to add them, and you're going to try to keep track of how many, if you were doing long addition the usual way, how many times you have to carry. So basically, what you have to do is you have to simulate the long addition process and just count. Okay, so they give you two numbers. They can be up to 10 digits. You don't actually want to know the sum. You want to know how many carries. So you have to actually do the long um, addition yourself. A few things that sort of little tricks, I guess. First thing is that um, you have to realize that these numbers are up to less than 10 digits. So if you want an integer variable would be good enough, but actually we don't really care because we don't even need the sum. Instead, we want to have an array of numbers or a string, and we want to be able to carry out our operations one digit at a time. You have to make sure that you do it from the last digit first, right? Because when you do long addition, you move from the right and go to the left. And then the other thing that is not apparent, perhaps, is that you have to be careful because there's nothing that says these two numbers have exactly the same number of digits. Okay, so if one of them has 3 digits, the other one 4 digits, then when you get to the fourth digit, you have to be careful that you don't read out of bounds, depending on how you actually represent this numbers. Okay, so I'll show you one way to do it the way that I did it. Why haven't I made any submission to this? Because I haven't logged in. Okay, let me log in. Okay. There we are. Okay, so I decided to have an array of integers, and I know that they're at most 9 digits. So actually, it's 9 is enough, but I guess I just did a couple more just in case. Um, so because there are multiple cases, I usually like to write my code so that the main would read in the input, and as long as there's another case to execute, so if it's not 0, 0, then I call a function that will actually do it. So that uh, helps me not get mixed up with the cases and the cross cases. Just make sure that every time I have a new case, everything is reinitialized. All right, so you give me two strings that are the numbers. I'm using strings to represent the numbers. I'm going to convert them to digits. So the way I do it is by using a loop that goes through every single character in a string. I increment the length to remember how many more characters I have, and I convert the characters to a number, to the value, by subtracting by the digit 0, the ASCII value of digit 0. And then I would have to remember that things are done in the opposite direction. I actually want to have the last digit first, so I reverse them, right? So that way the rightmost digit is at position 0 and so on. And the reason why I have extra digits here, it's actually because um, with the zeros, I initialize them to 0. So if I have an uneven number of digits in the two numbers, they'll just be filled with zeros anyway. Okay, so this is a little trick, I guess. It's a little bit subtle, but the fact that I have a larger than needed array and put zeros at the end means that I don't have to worry about two numbers that have different number of digits. Okay, so now that I've set everything up, so I just have to do my calculations. So go through all the go through all the digits. I only have to go through 9, I suppose. Although when you add two numbers, the result can be 10 digits. So there could be a carry still at the end. But anyway, that last carry could not have affected the result, so I could have stopped at 9. But anyway, I stop at 10 just in case. I have an answer, which is how many how many carries that I have done. Carry is whether currently from the last digits I had a carry. And then I just do the normal addition. For every single digit, I add the corresponding digit plus any carry that I had from previous step, right? And if the sum that I have, it's greater than or equal to 0, then carry is true, otherwise it's false. So this is a little bit, I guess this could be a Boolean instead of an int. But then it's a little bit tricky, I guess, to add a Boolean, even though, of course, everything converts between to 0 and 1. So anyway, I just use int. So sum greater than or equal to 0 is a Boolean evaluation. It will give you either true or false, which will also convert to 0 and 1. And I set it to here. And notice that I set it, and then I use the result of the assignment as the if statement, as the condition in the if statement. So if it's true, if there's a carry, then answer plus plus. I remember that I did one more carry, otherwise I don't do anything. And that's it. You might not like the way I wrote this. It's a little bit condensed and confusing if it's the first time you see it, because I'm testing, I'm assigning the results, and I'm using that result as a test. Most times, if you're a beginner programmer, they'll tell you never put an equal sign. Always remember put a double equal sign inside an if statements when you do comparison, because this means different things. And I'm actually here taking advantage of that meeting. So anyway, and then at the end, I just have to print the output, right? If answer is 0, then you print no carry operation. If the answer is 1, you print one carry operation. If the answer is more than 1, you print the answer followed by operations, right? So this is another thing that you have to be a little bit careful about to make sure that you really print exactly what you're supposed to print down to the last character. Okay, so anyway, that's first problem. It's not too hard, I hope. And of course, there are many different ways you can do this. And, you know, there are other ways you can do this, I'm sure. But this is perhaps a little bit more concise. Okay, let's look at the second number problem. Babylonian numbers. Okay, so this is actually, I guess, a standard problem where you're given a list of digits in a certain base, in this case 60, and you have to convert it into a different base, right? This time convert to decimal. So really all you have to do is figure out how to convert numbers from one base to the internal representation, figure out the value, and then convert it back. In this case, because it's just decimal, you just print it out and that's it. You don't even really have to convert. Okay. Now you do have to look at this and a little bit careful and say, okay, these are powers of 60s, and the 20 test cases, non-zero digits can be any number between 1 to 59, and 0 is represented by empty string. Okay, so already there's a little bit of a funny thing. That 0 is just missing. The number does not begin with a comma and contains at least one non-zero digit and consists of d digits in total, where d is 1 to 8. So there are at most 8 digits. So immediately you have to ask, are these numbers going to be too big? Right? What's the biggest number you can have? It's this. Just like what's the biggest, 9-digit numbers you can have in decimal? It's just a bunch of 9s, right? In decimal, the biggest number of whatever number digit you have, it's just a bunch of 9s. And in whatever it is called, base 60, the largest number you can have in whatever digit, with whatever number of digits, it's just a bunch of 59s. So already you have to ask, is this too big? Can you actually store this? Right, so you can just do a quick approximation. just to make it simpler. So it's less than 59 times 10, 60 to the 8 is actually just less than it. Is actually 59 times 60 to the 8 minus 1 or something like that. So let's just pull up a handy calculator. 59 times 60 to the 8 is this much. Is it going to fit in a 32-bit integers, even 2 to the 31 minus 1? That says normal int. The answer is absolutely no. What about 64-bit integer? So sine, the long, that's good enough. So that's the first thing that you should ask yourself is what data type should I use to store these numbers? And you should use a 64-bit integer. Okay, so long is good enough. You don't need. I know that the question doesn't ask for negative numbers, so you can even say unsigned long to get to 2 to the 64 minus 1, but you don't really need it, so we'll just not worry about that. Now, the second problem is how do you take these input apart, right? So it could be that you have one, the true showcase something like 1, 2, 3, 4. Okay, so you read it one somehow, but these, it's not just a single digit, it could be double digits. So you can't just say, read a character, next one is a comma, and so on. You actually have to read this whole number, get the next comma, read the whole number, get the next comma, and so on. What other problems are there? The other problems is missing numbers that are 0. So for example, if you say 1, comma, 3, that's really 1, 0, 0, 3. Or you can also have 1, 1, comma. You can end with a comma, and that's really the same as a 0 at the end. So there are lots of little special cases, right? Now, there are a number of ways you can do this. You can say, let's scan this string from left to right, one character at a time. And if you see a digit, then it's part of a number, you collect it. And as soon as you see a comma on the end of the string, you know that your number is done. And then if you see another comma, they have to say, well, have I collected any number yet? Etc. Etc. If you do that, you can make it work. But you'll basically have a loop from left to right, and inside the loop, you have lots of special cases. Right? Did I read a digit? Did I read a comma? Did I read a comma before? And what about this case where you read a comma, but then you're not done yet, but you ran out of string, so you have to remember that you need to also fill in the 0. And there are definitely ways to make this work. But I don't usually like to do this because there are just too many special cases to think of. So how can we do things so that we don't have to worry about special cases? We do this by making sure that there are no special cases. Okay, so this is a little trick, little way of thinking, I guess, that if you want to avoid doing special cases, you try to get rid of special cases. Okay, so how are we going to get rid of special cases? Special case number 1, when you see commas at the end. So if you see, excuse me, if you see commas at the very end, what do? Just add a 0, the character 0. Now you have no special cases. The other special case is if you see 2 commas in a row, what do? You replace by comma, 0, comma. I guess I should put these as strings. If you do these 2 tricks, right? So you might think that this is a little bit inefficient, right? You do check this, append a 0. Then you scan through the list, possibly multiple times, right? Because there could be multiple commas in a row. And every time you see 2 commas, you replace it by comma, 0, comma. And you might have to do this multiple passes. And in some way, you can say, yeah, this is inefficient because you have to go through the string many times. But at the same time, we know that this string has at most 8 digits. So, the Roe's upper bound would be like, there are at most 30 characters. It's not even that many, even if it's 30 or 100. So there's nothing wrong with going through a string of 100 characters 8 times at most. But the point is that even though you may be slightly less efficient in terms of runtime, you make your code a lot clearer because now, after the first 2 steps, it will only be always number, comma, number, comma, number, comma, and the last one is always a number. And now, the other trick then is that if we replace all the commas by spaces, like this, and because things are now separated by spaces, we can pretend that somebody typed this in from the keyboard and just read it. We'd run number at a time until we run out of inputs, and we will automatically get our 5 numbers. And the way we pretend that the content of a string, it's typed into the keyboard, it's using something called iStringStream, which we looked at, I believe, last week. So that's the first part, is how to take apart this input. The second part, you may or may not know this part already, is how do you convert a number from a certain base representation into the actual value. And that's actually something that everybody should know, I hope. If not, you should learn this. So it doesn't matter what base it is. So let's just say 1 times 60 cubed plus 2 times 60 squared plus 3 times 60 plus 4. Okay, so 1, 2, 3, 4 are the 4 digits. So at the beginning, you set the value to be 0. Okay, you haven't read anything yet. And we're going to read the digits from left to right. The first time we're going to take the value, 0, we're always going to multiply it by the base and then plus the next digit. So in this case, value is 0, so 0 times 60 is 0, plus 1 is 1. So after reading the first digit, this is what I get. Okay, value. It's 1. Now to incorporate the next digit, I'm going to take the value, which is 1 now, times 60, and that is going to give me 60, and then plus 2. So 1, 2 in base 60 is 62, right? 1 times 60 plus 2. And to incorporate next digit, what you do is multiply this by 60, whatever you had, plus the next digit. And everything would just work out because the 60 goes into the brackets. And then when you incorporate next digit, you multiply this by 60 again, you add 4, and then you get your 60 cubed, 60 square, 60, and 4, right? So this is a very common algorithm, I guess, that you should know in the back of your head, that if you want to convert any number in whatever base into the integer value, you can read it from left to right. And every time you add 1, add the next digit. You multiply it by base and you add the next digit, and you just keep doing that. Many people that are not as experienced would try to go the other way, right? So you have something, I don't know, you have something called b, which is set to 1, and then you would have answer. Every time it will be answer plus equals the next digit times b. And then b would be multiplied by the base, which is 60. And that is also going to work. You can go from right to left. And many people think of this as the easier way to think about. But it's harder to write, I suppose, because you now have to keep track of 2 variables and deal with 2 things. Whereas in the left to right way, once you're used to it, you can write that in just 1 line inside a loop. Okay, anyway, after all talking about all this, there's not much more to say. So let me show you my code. Oh, let me reload this. So I have okay, so again, I read in the number of cases, loop through that many number and call solve. So I read in the string S, and the first thing I do is I say that if the last character, so in C++, you can say S dot back, that's the last character. This will only work if the string is not empty. If you try to ask for the last character in an empty string, this can crash, so be careful. And then here, this is a little bit strange use of a for loop. Okay, so what am I doing? Remember, for comes in 3 parts. The first part is to initialize, the second part is to test every time, and the third part is to increment. I am doing none of that increment here, so what the heck is it doing? So first, I ask the string C++ string function find, do I see any commas? Okay. And find will return this special constants called string : and post if it cannot find it. So if post is not equals to this, that means it found it. If it doesn't find it, there's nothing more to do. There's nothing to replace. But if I found comma, then I got to replace it. And so what do? I call s.replace at the position. Replace the 2 characters, which are comma, by comma, 0, comma. Okay? Again, you can argue that doing string manipulation like replace and expanding the string like this all the time, it's inefficient, but I don't really care because the string is so short. And then to get to the next loop, I would ask again, do I have comma? And then I start all over again. If I don't have comma, I quit. Otherwise, I replace. So basically, this loop just repeatedly look for commas and replace them with comma, 0, comma. Now, some people would argue that this is actually a very bad abuse of a for loop, and they prefer to write it as a while loop and so on. I don't really care whichever way you want to do it. It's fine. I just write it here because it's easier for me to have a simpler body than no. Anyway, and then I use the stl function to replace all the commas to spaces. So all of that work, it's just to get rid of the special cases, and then now I'm ready to take apart the string. I use an istring stream. I have an answer, which remember is a 64-bit integer. And while I read in the next digit, I can use an integer because the digits are 0 to 59. I just say answer is equal to 60 times answer plus x. And then at the end, I just print it out. Okay, so I said a lot of stuff about how to do this problem, but at the end, the code is not too bad. But it's only not too bad because I took a lot of care into trying to figure out how to handle these special cases to make them not special. And also, the other thing you notice, and then maybe you noticed this from my other code before, is that I try my best to not reinvent the wheel, right? Writing using STL functions as I can. So if you, of course, you might not know all the STL functions that I do, but you have to start using them, and then the more you use them, the more comfortable you are with them, and little by little you'll learn how to use the system library. And imagine trying to write something like replace yourself. It's a little bit of a pain because you have to resize the string, you have to put things in the right place, but you don't have to worry about that here. And also, it's harder to get wrong because now you just read this code and you know that you're using replace, and you're not doing some, you're not writing some strange loop. Then you have to read it for a minute to figure out what it is that you're trying to do in that loop, right? Okay, so these are sort of, I guess you can say, trick of the trade. try to be more productive or more efficient programmer. And mostly is to make sure that you use the system libraries that are provided. Okay, lawnmower. All right, so you have these soccer fields, and this lawnmower will will cut strips like this. You want to make sure that given the dimensions of everything, so the dimension is always 100 long, 75 wide, but the lawnmower, the width of the lawnmower may not always be the same, and that's part of the input. You're told where the lawnmower starts, and you want to make sure that there are no gaps. Okay, so if there are gaps, whether it's going horizontally or vertically, then it's bad. Otherwise, it's good, like this. So you have to say, yes, there are no gaps, no, if there are gaps. They're going to give you numbers like these. Okay, and these, so in this case, you have 8. Where this person cut 8 times in the horizontal direction. Which way? Nx. Yeah, so the first the first nx numbers describe the end-to-end passes along the length of the field, and then the other ones, the next 11 ones along the width of the field. Okay, and you have to make sure that there are no gaps. The numbers are real numbers and have up to 7 digits after the decimal points, and any cat will also include its boundaries. Blah blah blah. Okay, so we have to figure out the algorithm and then how to code it. We don't really have to worry about how to do both uh, horizontal and vertical cuts, because if you know how to do one direction, the other one is basically the same. So we'll just deal with, let's say, just deal with this type of cuts. So it's between 0 and 100, 0 and 75, and they give you certain spot that they cut. They're also going to give you a W, which is a width of the field, the track. And this W, when they cut, it cuts a strip of W over 2 on each side. And you want to make sure that there are no gaps. Now, they can just barely touch, and that's okay. Or they can overlap, that's okay. But if they don't overlap and there's a gap, that's no good. So what should we do, right? So first thing to realize is that maybe we want to just scan these starting points in order from smallest to largest. They don't tell you that it's in order, so you have to sort them. And when is there a gap between the two, right? There's a gap between the two if the distance between these two is greater than W. If it's exactly W, you just touch. If it's less than W, you overlap a lot. But if the two starting points actually have distance bigger than W, then there's a gap, and that's it. So all you have to do to see if there are gaps between two lawnmowers passes is to make sure that successive starting points have gaps no more than W. If you find a gap bigger than W, you're done. But there's more. Because I just told you that this is how you check if there's a gap between two lawnmower starting point. But what about the two edges, right? 0 and 75. Well, here, if this gap, if this starting point is bigger than W over 2, then it's bad. So you need to make sure that the first one starts at W over 2 or less. And similarly, the last one has to end at 75 minus W over 2 or later. If it's ends earlier than 75 minus W over 2, then it doesn't cover that last bit. So that's the algorithm. The algorithm is sort, okay, check first one is less than or equal to W over 2. Check last one, it's greater than or equal to, well, 75 minus W over 2. Check gaps between I and I minus 1. And then I'm assuming that you don't check the first one or the last one because we already checked the gaps to the edge. It's less than or equal to W. If all of these checks are okay, then it works. And to check the other way is the same thing, except that this 75 is replaced by 100. Okay, so that's basically it. Now, there's a little bit of a sticky point. If you do exactly what I just told you, this problem will probably work, but you should always be a bit careful. These numbers, it says, has a certain number of whatever. Okay, so it's up to 100, I guess. So it can be up to 100, let's say, followed by up to 7 decimal points. 1, 2, 3, 4, 5, 6, 7. Now, if you represent this as floating points, then at this point you're going to ask, you're going to say, if, for example, this one, if the first one, whatever that, let's call it value x, if x it's greater than or equal to W over 2. Oh, sorry, less than or equal to. Now, W is a number like this, number with 7 decimal place. And the question is, are you going to have to worry about round off errors? Because why do we care about round off errors? Because we care about the equality, right? So if something is just exactly W over 2, you want to say, yes, it's okay. But when you rely on exact comparisons to make your decision with floating point numbers, you are potentially asking for trouble. Because when you do floating point computation, even when something is supposed to be completely equal, it might be slightly off. And then your comparison would be wrong. So there are two things you can do. Okay. One of the things you can say is, actually, there's three things you can do. One thing is you can ignore it, either because you decided it's okay or because you didn't know any better. And in this case, it probably works. I haven't tried it. And I'll explain why later. The other thing is to try to avoid things that can produce round off errors as much as possible. And you might say, well, instead of dividing by 2, maybe it's better to multiply. That may be better. It's not guaranteed, but it may be better. Or you can say, this is the way that I would do it. I know that this has exactly 7 digits. So if I read this number and I'd say this is the integer part and this is the fractional part, I can represent this number as I times 10 to the 7 plus f as an integer. So basically, I'm changing the unit of measurement here so that instead of saying I have, I don't know, 0.1 meters, I'm telling you that I have 100 millimeters. So here I'm making my unit measurement smaller, 10 to the 7 times smaller, so that I will only have to deal with integers. And actually, because I'm using divide by 2, I actually, in case this is an odd number, divide by 2 might not work. So in fact, I'm just doing 8, multiply everything by 10 more. Okay, so I'm just sticking a 0 at the end, basically, to make sure that when I divide by 2, I get no surprises. And that way, if I stick to integer calculations with this representation, I will not have to worry about Brownf errors at all. The drawback is that now I am above the range of a normal 32-bit integer, so I have to use long. But it's not much of a drawback anyway these days. 64-bit integers are widely available, so I might as well just use it. And that's kind of the thing that I want to bring up. It's not just that it's not just the algorithm itself, but also the representation. So here we are. So again, I have this solve function that runs every case, but I don't know when there's no more cases. So basically here I read in the number of x and number of y, and then I read in the width, which I write a function to read because it's a little bit tricky, I suppose. And then because I'm also going to read all the x and y values with the same function. If all of them are 0, that means I'm done because that's the x condition. Otherwise, I do something. So here, what am I going to do? I check whether I can do all of them. I got to do it in the x direction. I can do it in the y direction. I have this little funny thing here. Order matters. The reason is that in my check routine, not only do I check, I also read the input at the same time. Where is it? I read the input while I'm checking it. This function read the input and check it. So if I put it the other way, if I say oo equals to good, so good equals to good and check like this, if it already failed in the other direction, then this will be false. And short circuit evaluation C++ says that there's no need to evaluate this. And if there's no need to evaluate this, it will never call this function. It will never read the input. And then in the next case, they'll get all screwed up because they will still have the input from the previous case. So that's why I wrote it in this way. And I make a little comment to remind myself or remind people reading the code that it actually matters which way I write this. Okay, so how do I do this? So I multiplied the m, which is the 75 or 100, the limit that I'm looking at, by this 10 to the 8. I read in the positions with this read wheel. I sort them all. And then I do what I said before. I check that if the first one is greater than W over 2, that's bad. If the last one plus W over 2 is less than the limit, it's also bad. And then I check all the gaps. And I start at 1 because I'm going to check all the gaps and see if they're bigger than W. If any of the gap is bigger than W, I say it's bad. Otherwise, it's good. Okay, and finally, how do I actually read these numbers? I read it in strings first. Sorry, not the strings. I read it as integer. So I read an integer, the dot. It will stop at the dot. So I eat it up with the character variable, and then I read this. Now, the other thing, of course, is that it says the numbers may have up to 7 digits. So what if it doesn't have enough? Well, again, I like to avoid that special case simply by making sure that I have enough. So if I have less than 7, I make sure that I have 7. Just keep adding zeros until I have enough. And now I would take, now that I have this string of decimal digits, which have enough zeros, then I use the STL function s to long, string to long, to convert a string into a long, and then I convert into a big integer. Okay, so the algorithm requires a little bit of insight, perhaps sorting it and checking the gaps. But the other thing that you have to perhaps worry a little bit about is this floating point value. So let's quickly try something. We'll just use doubles. and we'll pretend that we don't have to do any of this long business. Let's see if it works. I think it's could work, and then I'll explain why that is. But I'm not absolutely sure. It's probably not a good idea to do it this way. Well, I shouldn't say it's probably. It's definitely not a good idea to do it this way. But let's try this just to see what happens. I change everything double, and then W is still there. Okay, let me just read it one more time to make sure I haven't screw up in what I changed. Everything's double now, double, okay. Okay, so let's submit and see what happens. Yeah, so it actually works. Now, why did I say that it probably works? And the reason is that even though we're doing floating point numbers and so on, and calculations, multiplying, dividing by a power of 2 is completely safe. Okay, why is that true? So to understand this, you have to understand how binary numbers, floating point numbers are represented. And basically it goes like this. And a floating point number could be something like this. A certain number of what we call mantissa, and then an exponent, you know, like this. It's basically scientific notation in binary. So for example, 1, 2, 3, 4 times 10 to the 4. This is the same thing as, of course, 1, 2, 3, 4, 0. Or if it's 0.123, like 0.01234, then that would be 1, 2, 3, 4 times 10 to the minus 2. Okay, so when I say that you can have round off errors, what can happen is that when you do something with the operations, you have a certain number of digits that you can store in the mantissa, and you run out. You need 10 digits, but you only have 8. So what do? You lose the last 2 digits. Okay, and that's how you get round off errors. But when you're in the decimal notation, let's say, if you multiply and divide by 10 or any power of 10, you don't actually touch the mantissa at all. All you do is you update the exponent. And these are integer. You multiply by 100, you added 2. There is no round off errors. Similarly with binary, when you multiply and divide by powers of 2s, there are no round off errors because the mantissa is never touched. Now, you can lose precision when you do subtract and plus, right? When you do plus, maybe you have 2 numbers here and you add them and then subtract them, you can lose precision that way. But because we only do one, we're only doing one single addition or subtraction at most, you're not really going to have a problem. You're not going to lose precision that quickly. Usually you have to do a sequence of operations and then things start to, the round off error starts to accumulate. So because the operations are so simple, you actually don't have to do any of the stuff that I told you about. It will still work, especially because you divide by 2 and not divide by anything else. If you have to divide by 3 or 5 or something like that, then it could be affected. Okay. So the fact that you only have to worry about multiplying and dividing by 2 in this problem saves you even if you didn't know. So in this case, unfortunately, if you are blissfully ignorant about these floating point numbers and just do it, it will still work. But it's good practice to at least think about what's happening. If you're not sure, use the safe thing. So this is one of those cases where if you don't know anything and just do the easy thing with doubles, it will work. If you think a lot, realize that you're only multiplying, subtract, and then dividing by 2, you realize that you don't have to do anything special. It will still work. If you kind of know something, that you shouldn't just rely on floating point, but not know enough that you know that it's okay, then you have to end up doing a bit more work and make sure it works. But it's a little bit strange that if you just look at somebody's correct code to try to learn from it without all that sort of context, you wouldn't know why it is okay to do the sort of obvious thing, which is to use doubles. Anyway, so I don't know. This is like just me droning on about something that end up not being very important in this problem. But in practice, you should, every time you see a floating point number problem, you should always ask, do I really want to use floating points? And most of the time when you see um, comparisons relying on the fact that if it's equals exactly equal, you want to do something, otherwise do something else, you have to be extremely, extremely careful. Okay, texture analysis this time. You're given this pattern. You want to know if the number of dots between each pair of stars is the same. I don't really have much more to say other than you can scan this from left to right, and then you just remember. So this is something that reads one line at a time and called a solve for each case. And then here I just remember where's the last star that I've seen, where's the gap size that I've seen. -1 means I've never seen one, and then I just process. The last, it always starts with a star. That's why last is 0. And I look at the second character at position 1. If it's a star, then I have to do something, otherwise I don't. Then I compute the size of the gap since the last star. If I have never seen a gap before, then now I remember the gap size. Otherwise, if I've seen a gap before and the gap size is not the same this time, then I print not even. And then I remember if I don't quit, that means the gap size is still okay. I update where the last star is. That's the current one, and then I move on. You can look at this code. The cat is somehow don't indent things quite completely properly. I don't know why when I uploaded it. So anyway, maybe this looks better. Okay, something like that. Okay, the last one is one that I want to. This one is one that you have to think more about, perhaps, and the sort of algorithmic side, and it's meant for some, I think, people that may have done 3620. So anyway, let's see. You have an array with integers in decreasing order, so it's sorted backwards, and a list of pairs A1, B1, A2, B2. You wish to sort the array A in increasing order. Each time you choose an I can be chosen multiple times, and swap AI with a BI. Determine whether this is possible. You have N and K. K is the number of pairs that you can swap. N is the number of elements in the array that most 1 million. So here, for example, you have 5 things. You can swap between the first one and the last one, the second one, and the fourth one. And if you just do these 2 swaps, you will sort an array from decreasing order to increasing order. And then in this case, they give you an array and a bunch of pairs, and there's no way you can actually swap them with these pairs, no matter how many times you do it, to get to a sorted array. Okay. It doesn't really matter what the elements are, so we might as well just pretend that they're 1 to n, but backwards. How many am I? This is 12, so it's like 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And obviously you need to convert them to 1 to 12. So what happened, what you need to do is to figure out, can you move 12 somehow? Who knows, maybe go back and forth to this position. right? Because if there's no way that 12 through a bunch of swaps can shift eventually to this position, then there's not much you can do. At the same time, though, if you can move 12 to the last position, you can basically take the 1 backwards and move 1 to the position it wants. So if you think about these indices, as nodes in a graph, and there's an edge between nodes if you can swap them, right? So 4 can go to 7, 7 can go to 8, 8 can go to 6, 5 or whatever, and 5 can go to 12. We're asking, is there a path from 1 to 12 and 12 to 1? If there is, then it is possible. It's okay. Maybe I should go backwards. If there's no path from 1 to 12, there's no way you can ever take this 12 to the correct position. There's no way you can ever take the 1 to the correct position. End of story. But just because there's a path to do it doesn't mean that you can do it. Why? Because maybe when you move the 12 to here, then 1 will somehow, as you move things, 1 will can 1 get stuck somehow and then won't be able to move backwards. So you have to be a little bit careful about that. And the answer is no, you can never be like that, because once you have a path, whichever path you have, you can swap it. You know, these things, you can kind of do a bubble sort on this path to make this path sorted. The things that are in this path sorted, kind of doing like a bubble sort. And you will always be able to take things in here to here. Okay, great. So 1 and 12 you can sort, right? And then basically you want to know if there's a path from 1 to 12 somehow by touching multiple places perhaps or directly, if there's a path from 2 to 11, 3 to 10, and so on. How do you know if there's a path? You can use depth first search, for example, to see if they're in the same connected component, etc. Or some other ways to decide if they're same, that you can reach each other. But what you cannot do is for each pair find a path, because there's a million entries that's going to be too long. You want to do some processing that allows you to answer this for every pair quickly. And one way is to use depth first search to identify which ones are in the same connected components. And then once you identify all the connected components, then anything that are in the same connected components can be to each other. Now, things that are not in the same component don't interact with each other, but things that are in the same component could interact with each other. And now you have to be a little bit careful. So for example, let's say you have a path that goes from here to here, then to here to, let's see here, 6, to here, to here, to here, and then here. Okay, so there's a path from 1 to 7 to 4. So hang on. I'm kind of messed up here. So this should be here. 1 to 7 to 4. Wait, hang on. I'm messed up with my, let me draw this again. 1 to 7 to 4 to 6. And then let's say to 12 to uh, Okay, does this work? To 8. That doesn't work. So I have, no, hang on. 6 and 7. Okay, 6 and 7 are okay. 1 and no, not to 8, to 9. That's okay. Okay, so I have a path from 1 to 7, 4, 6, 12, and 9, like this. So I can swap 1 and 7, I can swap 4 and 6, I can swap 12 and 9. Now I have to be a little bit careful, because if I just swap 12 to this position, how do I do this? Well, 1 to 7, so 1 and 7, so 6 got here. And then 7 to 4. 4 to 6. 6 to 12. And wait. Okay, so now I got the 12 in the right place. Now at some point, I'm going to need to move what number into here? 9. So how do I move 9 to here? 9 has to swap position 7 to 4, 4 to 6, 6 to 12. And now you move the 12 out of the place that it's supposed to be. And then you move here. So the 12 here, even though I move it in the right place, it might still have to be moved later. And that could be a problem. Because just because you move 12 to the right place doesn't mean it works. And the trick is to not just look at 12 because this is the last position. Don't move that first. Even though bubble sort says move the biggest one to the last one, you actually do bubble sort on this path. So you actually move what is supposed to be in this position first. Because according to this path, whatever is here is the maximum. So the way that we think about the largest one in the path is actually this one, not 12. It's the 9. You want to move the 9 to the right place. Once you move that, then you can move the 12 and this will never be disturbed again, and so on. Now, so that's what you have to do to show that if you have a path, then you can actually sort everything on that path. You're not required to show this because you're not asked to actually give a sequence of swaps. You're just asking yes or no. But it's good to convince yourself that if there's a path, actually everything will work. Okay, but there's more than just a path. It could be, even more complicated, even cycles and so on. What about that? Maybe there are multiple paths. Well, it turns out that you can just take the path, get all of these things in order. Okay, then you can take some other path that involves things that are not in order yet, sort it will still work, and so on. And eventually you will use the same argument, it will work. Again, you don't have to do this because you're not asked to actually produce a sequence of swaps. But why are we even doing this? Because we want to show that you can sort if and only if, I guess you can say this one, position 1 and n-1 in same component, it's connected. 2 and n-2 is connected, and so on. All of them, all the pairwise are connected. And this, if I just use the first argument that says, well, if there's no path, you cannot do it, that only shows you that if you can sort, then you must have the second part. So in other words, the second part is a necessary condition, but it doesn't say sufficient. Just because you can do this doesn't mean you can sort. So the argument that I spent quite a bit of time working out, basically tells you that it's an if and only if condition. So you only have to, at the end of the day, you only have to check if position one and n minus one is connected and so on. So I guess English are connected. And different ways you can do it. The way that I did it in my code, it's the standard way that you learn in 3620, which is depth first search. So I read in a graph, I read in using what we call adjacency list. So read in a graph, I run a DFS on anything that's not labeled. So if you have never seen this before, read this, even if you have no DFS but haven't seen how you code it, read it carefully. And this basically will label each node with a number that's unique to the component. So everything is connected to the first node would have component 0. Everything that's connected everything that's not connected but connected to something else might have label 1, label 2, and so on. And then at the end, I just ask for each value, it's label with the two things at either end the same label, meaning that they're connected. If you want, if you know what this is about, if you heard of this, you can just use the label. You can find these labels in a different way instead of depth first search, using something called union find of disjoint set data structures, and that's in my code library. But that's perhaps for another day. Okay, so that's kind of concludes all what I want to say. For sure, the last problem, swap to sort, is significantly more involved in both algorithmically and computation, algorithmically and then implementation. But I would say the first two and the fourth problem probably don't need much knowledge, algorithmic knowledge, I mean. Problem C will require a little bit. And then if you were to do it, I would strongly suggest that you try doing it with the integer instead of just the floating point. But maybe you want to do the floating point first just to make sure that you can get it done before you try to convert to a floating point. Anyway, I guess that's it for this week, and I'll see you again next week.